In this video, we address two variable or bivariate relationships. Two forms of bivariate analysis that are common: contingency tables or cross-tabulations, and correlations. Remember, in bivariate relationships, the variable to be explained we call the dependent variable, and the variable that is to do the explaining, that we're viewing as the cause, we call the independent variable. So if our variables are education and income, which is which? Which is the dependent, which is the independent? Well, commonly we would think that education would have some kind of causal impact on income. Indeed, the greater the education, the lower the income? No, of course not. We're assuming the greater the income. Most of us likely in this class are assuming that getting a degree is going to improve our financial circumstances, which on the whole I think is quite correct. So the dependent variable in this case would be what? Income. That's what we were trying to account for variation in, and one of the variables that we're saying has an effect, has an influence on income, is education, whether it's years of schooling or more likely degrees or diplomas attained. Now let's look at a crosstab or a contingency table. You're a researcher and you're interested in examining the determinants of job satisfaction. Obviously, people vary in the extent to which they like their job. One of your immediate questions concerns whether satisfaction is influenced by the sex of the worker. Specifically, are males more likely to be satisfied with their work than females? And so we have here a set of data. So we have two variables, sex and job satisfaction, and each of them have two attributes, men and women, of course, for sex, and to keep job satisfaction simple, we'll just say it's high and low. Now, just looking at this table here, what can we say about that relationship? Are men more or less likely than women to be satisfied with their work? It's rather hard to tell, isn't it? You have on the ends varying sizes, and that makes it a little difficult to just eyeball and come to any kind of conclusion. So that's where a contingency or crosstab comes in. There's 6 basic steps that I've outlined here in generating a crosstab. Number 1, you have to determine which is the cause and which is the effect. Number 2, you place the cause, the independent variable, in the column position and the dependent variable in the row position. Next, you place the numbers, the values, in the table cells. Fourth, you calculate the total for each attribute of independent variable by summing the distribution values for each cell for that variable. Fifth, you calculate a percentage for each cell by dividing cell value by column total. And then the final stage is to compare cell percentages across rows to determine the extent of variability or the effect of the independent on the dependent variable. Now, this may seem a little complicated, so I'm going to go through each step with you. So here we have our independent variable and each attribute, x and y. Our dependent variable, each attribute, a and b. And then we have, in the middle here, a crude, if you will, frame in which we're going to plug in our numbers. But remember, the first task is to determine which variable is the independent and which variable is the dependent. Typically, the independent variable we place in the column. The dependent variable is in the row. So let's determine where sex and job satisfaction should be placed. Which is the independent variable? Is it sex or job satisfaction? Of course, the answer is that it's sex. And the attributes for sex are men and women, and job satisfaction is our dependent variable, and the attributes are high and low. So this task involves now placing the numbers or the values in appropriate cells. So let's go to the next table to place the values in the cells. How many men have high satisfaction? We find that 90 do. 60 men have low satisfaction for a total of 150 men distributed across those two satisfaction levels. For women, we found that 110 have high satisfaction, 40 have low satisfaction, for a total, again, of 150. Now, of course, these numbers are not always going to be equal to one another. Typically, they're going to be rather unequal. We'll have, in the case of an independent variable, we'll have one attribute having more than the other. But just for purposes of simplicity, again, I'll make them equal here. Okay, now the next step is to find the percentages, right? So for 150, what was it? For those men who have high satisfaction, what percent are they in terms of the total? And of course the answer is they're 60%. What percent of the total of men have low satisfaction? The balance, of course, is the answer, 40%. And those percentages must add up to 100%, or 99.9, or 100.1, if there's some kind of rounding error in terms of percentages. For women, of the 150 women, we found that 73.3% have high satisfaction, and the balance, 26.7, have low satisfaction, for a total of 100%. So fine. Sixth, compare cell percentages across rows to determine extent of variability. So again, looking at those percents for men and for women, what does it say about the effect of sex on job satisfaction? Well, clearly most men and most women like their jobs. They have high job satisfaction. So that's clear to say. But does one sex have greater job satisfaction than the other? And as we can see, yeah, women have almost 75% of them. About 3 out of 4 women have high job satisfaction, whereas only 60% of the men do. So there is a difference. Now, whether these are significant, statistically significant differences or not, remains to be determined through the calculation of a statistic such as chi-square. But at any rate, we do see that women are more satisfied on the whole than men. Now, another way of looking at bivariate relationships is to employ correlation. And correlations relate to the association or the covariance of two variables with each other. To use correlation, the variables have to be at least at the ordinal level of measurement, since
correlations involve at the very least rank order. So we couldn't use correlation analysis for nominal level data. Generally, we wouldn't use them, I should say. Commonly, a correlation is represented in the form of a correlation coefficient, ranging anywhere from 1.0 to a minus 1.0. Now remember, correlation in and of itself does not prove causation. If a variable is correlated with another, it may be a completely spurious relationship, that is kind of an accidental or random relationship, just by coincidence, or it could be a causal relationship quite possibly. Now, the simplest way of looking at bivariate relationships, aside from using simply a correlation coefficient, which is a value, a number indicating correlation, is to use a scatter plot. Notice on our x-axis we have schooling, and our y-axis we have age at death. We're assuming that education or schooling will have some kind of effect on longevity, right? And typically we put the independent variable on the x-axis, and on the y-axis we put the dependent variable. Is there an association between educational attainment and longevity? That is, do better educated people live longer than less educated people? Okay, so let's say we get this image, we get this kind of distribution through our data. Now each of these little stars, if you will, represent a person who has died, and their level of schooling, and their age. And so this person had very minimal education of about 3 grades and died somewhere around 70. This person over here had well over 20 years of education and died somewhere in his late 30s or early 40s. Now, what does this distribution pattern suggest? Does it support the proposition or hypothesis that education has a direct relationship with longevity? Of course not. It suggests, in fact, just the reverse. Those with greater education, in fact, tend to die younger, whereas those with lesser education tend to live much longer. What if we got a distribution pattern like this? It appears those people, those data points, are kind of randomly distributed. So that means that there doesn't appear to be a relationship between the two variables. And then finally, what if we got a distribution pattern such as this? What would that suggest? Those with lower degrees of education tend to die younger, and as we move up in education, we notice that age of death also tends to increase. So people with more schooling tend to live longer, which would support our original hypothesis. Okay, that's all I wanted to say about bivariate relationships at this point.